Alright guys, okay. Okay, there's another lab that we're running tomorrow for this lab 1. So for those who are scheduled to attend tomorrow's class, please remember to come with the lab manual, which you can download from the course site. Okay, print a copy and bring along. Okay, for those who missed the lab, okay, we would try and see whether we can arrange for makeup. Okay, we'll inform you later. So for those who missed the lab 1 session, you are not allowed to just attend any one that we're running. That means for tomorrow's slot, you cannot just come in. Okay, it's not allowed by MOE, so please wait for information on makeup sessions. Okay, so let's get started with a quick review of what we have discussed in the last lecture. So, okay, so we talk about in the case of a free particle, right? Like a particle in an atom, and if you actually solve the Schrödinger equation, you find that the energy against the momentum of this electron, okay, it's actually having a parabolic relation. The only difference is that the energy of this electron in an atom, it's actually discrete in nature, and you find that they are actually comprising of this point solutions, right? Okay, the energy against the momentum relationship of an electron in an atom is actually this single points that you see, okay, discrete values, but the overall relationship is still parabolic in nature, like a free particle in classical physics. We sort of briefly discussed in the case where you extend this analysis to the case of electron in a crystal, right? We find that it's in general no longer a parabolic relation between the energy and the momentum. In this case, in quantum mechanical particles like electron, we basically investigate the relation between the energy against the wave vector. Okay, the wave vector is related to the momentum of the particle, right? Okay, so typically we would study the relationship between the energy and the wave vector. In other words, we look at the EK diagram, and we can see that they are, generally not purely parabolic, but comprises of this different curves that you see, okay, which somewhat resemble a parabolic relation at a certain part of the curve. So this EK relation is actually symmetrical, okay, about the origin, which means that if you know half of it, you can essentially know the other half because they are symmetrical, right? So wherever we show the EK diagram of a semiconductor crystal, we usually just take one side of it and we piece it together with the EK relationship in different directions. Okay, this EK relation, it's actually different in different direction of travel in the crystal, because if you think about it, in a certain direction that you go, the spacing between the atoms is of a certain value. If you move in a different direction, the spacing will change. Okay, and the spacing change, you affect your Schrödinger equation solution, and that will lead to a different EK diagram, right? So if you piece these different ones together, it gives you a sense of how an electron actually behaves in terms of the energy versus the momentum in the crystal. Okay, so this is helpful to describe how the electron actually moves in the crystal. So if you look at textbooks, okay, typically the EK diagram would have a different direction that's specified. Okay, that's all pieced together, and it looks something like this, right? So if you look at the EK diagram of different semiconductor, you will notice specific characteristics of this EK diagram. Okay, you find those where the minimum point of your conduction band occurs at the same K value of the maximum point of your valence band. So in this case, we call such a semiconductor a direct bandgap semiconductor, and we explain that for this type of semiconductor, the condition for electron to move from the conduction band edge to the valence band edge, okay, it's highly probable. Okay, highly probable in the sense that it can occur readily because conservation of energy can be satisfied, and you also have conservation of momentum. Okay, so if these rules are actually satisfied, then there's a chance that the electron can actually recombine to get back down to the valence band. And in this process, you actually find that a photon is actually emitted. Okay, a light is actually emitted. On the other hand, if you look at other ones where the minimum of the conduction band edge and the maximum of the valence band edge, it's actually at different K value. And for the electron to get from conduction band to valence band, it requires a change in momentum. Okay, so by itself, this cannot just happen, right? To conserve momentum, the total momentum must be equal to 0. Okay, so in other words, this change that's required to move an electron from the conduction to valence band has to be countered by momentum that's in the opposite direction, right? So if that process itself can involve another interaction that cancel out that change in momentum, then this direct recombination process can occur, and you can have a photon emitted. Okay, but of course, to find to be involved in another process where you could counter this momentum, it's actually quite challenging, because although technically speaking, this electron can gain the momentum from vibrating atoms in a crystal. Okay, you must find one that exactly matches the amount that it needs to cancel out. Okay, so the chance of actually such an interaction is quite low, although possible, but it's low. Okay, so instead, what you find is that this electron will tend to get back down to the valence band by going through what we call defect states in the band gap, which exists because of imperfection in the crystal. Okay, it turns out that semiconductor crystal, practical ones, there will be some imperfection in terms of missing atoms in the lattice, or you have extra atoms in between lattice, and that would basically change the sort of energy structure of your semiconductor. Okay, so it changed in the form of introducing additional energy levels in the band gap. Okay, so this energy levels in the band gap helps to mediate the transition back down. Okay, so this electron can move through this defect states in the band gap, right? So in going down to the different defect states, it loses energy in the form of heat to the crystal before it gets back down to the valence band. So you can think of this as having two competing processes, right? One is through the defect states, where it goes down by releasing heat to the valence band. Of course, the other process that is possible for it to get back down to the valence band is a direct transition from conduction to valence. In doing that, in fact, it gives off a photon. In the case of indirect bandgap semiconductor like this, you find that the direct band-to-band transition is harder to occur, right? The chance of it occurring is not high compared to if you were to go through this defect state. Okay, so between these two competing process, the one that go through the defect state is of a higher probability. Okay, that means the chance of it occurring is higher, and you find that for such a semiconductor, it doesn't emit light so easily. Okay, because it tend to go back down to the valence band by losing energy in the form of heat through the defect states. Okay, in fact, in the direct bandgap semiconductor, you also have defect states. Okay, again, it's a competition between the two. In the case of direct bandgap, this band-to-band transition occurring, it's actually quite easily satisfied, right? The conditions are easily satisfied, so it's quite easy for the electrons to go from conduction to valence band directly. Of course, some will go through the defect states, but because this band-to-band transition has a higher probability, you get actually a lot more photons emitted compared to energy that's lost in the form of heat through the defect states. Okay, so in reality, in both types of semiconductor, these two processes are there, right? It's just that which one is actually having a higher probability. In the case of direct band gap, it's higher probability, and that makes it actually a good emitter of light. So what you find is that in applications that require light emission, like LEDs, laser diodes, typically would use a direct band gap semiconductor, okay, because you can get light emission very efficient compared to indirect band gap semiconductor, okay. Now, one other thing that we talk about is that although the EK diagram of a semiconductor it's no longer parabolic, okay, but if you look at where electrons and holes generally occur in the EK diagram, for most application, they tend to exist near to the edge, okay, of the conduction band and the valence band for electrons and holes. And if you look at those region, right, this region here is still approximately parabolic. Okay, the same goes for the valence band. Okay, if you go near the edge, this portion here is still approximately parabolic. Okay, so a lot of times in many of the applications, if you want to analyze how an electron moves, right, and you need to sort of describe the behavior, right? We kind of use this parabolic approximation, okay, so that you can put classical parameters like a mass quantity to describe its motion in the semiconductor. Okay, and that's precisely where the effective mass comes from, right? In order to describe the motion without having to bother about this internal interaction with lattice atoms. Okay, we actually try to determine sort of equivalent mass quantity that allows you to use classical descriptions, okay, like F equal to ma, to describe how electron, for example, moves in the semiconductor, right? Okay, so, and it turns out that because near to the edges of your conduction and valence band is approximately parabolic, we can actually use the classical descriptions of mass, okay, because if you differentiate the energy against the momentum curve twice, okay, that curvature quantity, right, actually relates to the mass of your particle. Okay, so in a classical sense, if you have this parabolic curve and you differentiate this twice, then you find that the curvature value that you get is related to the mass of the particle. So similarly, in the case of electron in a semiconductor, if you use the EK diagram and you do a second derivative, right, to get a curvature, that allows you to derive mass quantity so that you can use classical description, right, to talk about how it moves in the crystal. Okay, and that's simply because there's a parabolic relationship at the edges, so we can use that same equation. Okay, anyway, this effective mass is something that you can use to describe, fundamentally describe the motion of electrons or holes in the semiconductor. Okay. Right. Then we have also talked about intrinsic material, right? In a pure semiconductor material, where we say that the free electrons and holes that you find in the semiconductor comes from a direct transition from valence to conduction band, okay, giving you a free electrons and a free hole. So the free electron basically can move in the conduction band, and the hole can move in the valence band. All right. So the way we visualize this is that, of course, for electron, it's like a sort of classical particle, right? If you accelerate this with some external force, for example, the energy of this particle will increase, and you'll find the particle moving upwards in the band diagram. Okay, remember the band diagram vertical axis is energy of electron. In the case of hole, if you apply a force and you cause it to move so that it increases in energy, then this hole will basically move downwards. Okay, unlike electron, the increasing energy for hole is downward because the charge is different. Okay, so a way to sort of better understand this is to think of a hole as like a bubble, right? If you think of a bubble, the bubble tends to flow out, right? So if you try to push the bubble down, you need to exert energy to push it down. If you do that, then the bubble will gain energy, so to speak. Okay. So the way you can try to understand its behavior is by considering the hole as like a bubble, okay? So in such a pure semiconductor material, you'll find that the number of electrons that's in the conduction band is always equal to the number of holes in the valence band, because the process where these free electrons and holes are created is due to this band-to-band transition. Okay, so every electron that's produced, it always gives you a hole. So in other words, the concentration of electrons, in this case denoted as Ni, because it's intrinsic. Okay, the N subscript I is to indicate that it's intrinsic. It's always equal to the whole concentration, okay, of the intrinsic material. By the way, this concentration, right, electron and hole concentration has units of number per unit volume. Okay, so typically we express it in number per centimeter cube. Okay, typically we use centimeter as a unit of length in the concentration quantity. So it's how many you have per unit volume in the semiconductor. Of course, by itself, this pure semiconductor is... Yes, anyone got a question? Anyone has a question? No? Okay.
Hi, Prof.
Yeah.
Can you record the lecture?
Okay. Right. Okay, give me a minute. Okay.
Thanks, Prof.
Right. Okay, so of course by itself, the pure semiconductor material is actually not so useful, because in order to make a useful electronic device, a semiconductor device, you need to have varying concentrations of the carriers. Okay, so in order to change the concentration of carriers, okay, we actually have this additional process that we would use, which is what we call doping, where we introduce impurity atoms into the crystal, right? So there's actually two types of impurity atoms that you can put to the semiconductor to introduce either electrons or holes. Okay, so in the case where we want to make these electrons, right, as the larger number of carriers, what we do is that we put in group 5 elements into the semiconductor material. Okay, so when you dope it with group 5 elements, for example, in this illustration here, we put phosphorus atom, which is a group 5 element, in place of silicon atoms in the lattice. Okay, so typically this will spread out throughout the semiconductor. And what you find is that with a group 5 element in the semiconductor, it actually has a loosely bound electron, okay, which does not participate in the bonding. And this fifth electron is actually loosely bound to the phosphorus atom. Okay, and the energy of this fifth electron, when it's bounded, it's actually at a level called the donor level, just below the conduction band edge. When the temperature of the semiconductor crystal is sufficiently high, you find that this fifth electron can break off from the impurity atom, right? It can become a free carrier in the semiconductor. And in the Venn diagram, it corresponds to electron moving from the donor level to the conduction band. Okay, in doing that, it becomes free electrons in the semiconductor. Notice that in this process, it actually do not produce a hole in the valence band. Instead, it actually leaves behind an ionized impurity atom that is stuck in the lattice position. Okay, so this phosphorus atom actually become positively ionized, and it's different from holes in that it doesn't move, right? Because it's fixed in the lattice position. Of course, in this type of semiconductor, your band-to-band transition is still occurring, right? Because this is an intrinsic behavior in the semiconductor. So you still have this band-to-band transition where one electron from a silicon-silicon bond can break off to become a free electron, leaving behind a hole. Okay, this process is still there. But if you compare between this and the ionization of the dopants. The ionization of dopants actually occur more readily because the barrier that exists, to the conduction band is a lot smaller. So as long as you have sufficient, a little bit more thermal energy, right, you find that this ionized dopant or this impurity dopant will actually ionize very easily. Okay, so this actually ionizes very easily. So if you put a sufficiently large number of phosphorus atom in the crystal, then you can basically control the number of free electrons you have in the semiconductor. Okay, and of course in this case, you will expect that with more electrons than holes. We call this an N-type semiconductor, where the electrons are the majority carriers and the holes are the minority carriers. Okay, and we can write down this equation here, N naught equals to ND plus P naught, which is called the charge neutrality equation, to describe the relation between the concentration of electrons and the concentration of holes in this semiconductor. Okay. So similarly, if you want to introduce holes into the semiconductor, we introduce a group 3 element into the silicon lattice. And in doing that, the group 3 element will only form covalent bonding with 3 nearest neighbor of the silicon. There's a fourth one which it doesn't have enough electron, right? Outer shell electron to share with. And that basically result in incomplete bond. The energy of this incomplete bond corresponds to the acceptor level, right? That you see in the band diagram that is just above the valence band edge. And if you have a non-zero Kelvin temperature, right, then you find that neighboring silicon-silicon bond can break off, and the electron can actually come to fill up the incomplete bond between the boron and the silicon. And in doing that, you find that the boron atom become ionized because it has now one more electron, so that makes the boron atom negatively charged. Okay, so similar to the phosphorus doping, this boron atom actually cannot move, right? Although it has a charge, it cannot move. It doesn't contribute to current flow, right? It just causes a part of the semiconductor to carry a charge, okay? And in that process, it leaves behind a hole between the silicon-silicon bond, and this hole can move freely. So in this process here, actually you do not get electron that is produced. You only introduce holes into the valence band, okay? And this allows you to change the number of holes in the valence band by controlling how many boron atoms you put in the silicon crystal, all right? And similarly, you still have that band-to-band transition. Unlike your N-type semiconductor, you have now more holes compared to electrons, and we call this a P-type semiconductor, where the majority carriers now are the holes and the minority carriers are the electron. Similarly, we can write a charge neutrality equation that relates the electron and hole concentration via the doping concentration. That means how many dopant atoms you put into the crystal per unit volume. All right. So these are the two main processes, right, that we can independently change the electron or hole concentration. Okay, we also sort of briefly talk about the temperature dependence on the carrier concentration in a doped semiconductor. And we see that the change, okay, basically corresponds to how this mechanism of band-to-band transition and the ionization of dopant atoms dominates in different temperature range, right? So in the initial temperature range for silicon, like 0 to 150 Kelvin, this increase in your free carrier concentration, the electrons, essentially due to the ionization of your dopants, right? Because the temperature is still relatively low, the band-to-band transition number is not very high because the barrier to overcome it's very large. Okay, so at low temperature, this doesn't occur very readily. On the other hand, fifth electron in this case for the impurity atoms is very close to the conduction band edge. Okay, so the barrier is a lot smaller, right? So at relatively low temperature, you find that the dopants can ionize very easily. And that basically causes an increase in the electron concentration. And once you go to a temperature between 150 and 450 for silicon, you find that the concentration actually stabilizes, right? because this corresponds to the range where all the dopants are ionized, so there's no more impurity atoms that can contribute electrons. It's all promoted to the conduction band already. Of course, you still have this band-to-band transition, which is still increasing slightly, but the increase is not very fast because the temperature is still relatively low. And as a result, the number of free electrons in this case is contributed by the dopant. Okay, so and the doping that you put in the semiconductor is fixed, right? So you expect this value to more or less stay a constant. Of course, if you zoom in, you do see it increasing a little bit, right? Because the band-to-band transition is continually being increased as you increase the temperature. Only issue here is that the increase is small at this temperature range. So we call this the extrinsic region, right? Where the semiconductor behaves like an extrinsic material. So it's not a pure material anymore. Once you go above 450 Kelvin for silicon, you find that the temperature now is so high that the band-to-band transition starts to become quite a lot, okay? And you get a lot of electrons at holes that is being created, so much so that it starts to dominate the number of electrons and holes in the semiconductor. Okay, and you will find that above 450 Kelvin, the concentration of electrons and in fact also the holes will start to increase. Okay, and this dominates the total concentration of the carrier. And in fact, in this region here, it's called intrinsic because the band-to-band transition number is so large that it dominates the total number. Okay, the doping concentration, okay, the amount that you put in, right, is no longer significant. Okay, instead, it's the band-to-band transition that becomes significant. And in fact, in this region, the number of electrons and holes are approximately the same. Okay, so it kind of revert back to the pure material characteristic. All right. So of course, in a lot of the application, we usually try to keep the semiconductor in this extrinsic region range because a lot of times devices are basically designed to operate, in this using this fixed doping concentration, right, to give you the desired behavior for the devices. Okay, so typically we keep it between the extrinsic region. So you try not to have the device or have the whole system operating in a temperature outside this range. Okay, because once you operate outside, then the concentration changes, the device behavior will not be what you intended it to be. Okay. Right, so for today's discussion, we're going to look at how to calculate, or in fact, how to derive the concentration of electrons and holes in the semiconductor, okay, from basic fundamental derivation consideration. This is important because when we describe the current voltage characteristics of semiconductor, the important part here is the number of carriers you have in the semiconductor, right? Because current relates to how much charge is flowing, right, per unit time, and how much charge there is in the semiconductor will influence this. Okay, so the number of free carriers in the semiconductor is an important parameter that we need to know how to calculate. All right. So as I mentioned, there is these two concentration that we need to worry about. The first is your electron concentration in the conduction band, because these are the guys that will move when you have a force. Okay, and the movement will result in current. Similarly, the whole concentration in the valence band, these are also charged particle that can carry current. Okay, this is also the other important parameter that we need to know how to calculate. Okay, so for today's discussion, we are focusing on what we call thermal equilibrium condition, where if you recall, right, previously we say that this corresponds to the case where there's no external force. Okay, so there's no voltage, there's no electric field, there's no magnetic field, or even temperature difference in different parts of the semiconductor. Okay, so you'll be basically a semiconductor that sits on the table, right? That you don't have anything influencing the carrier in the semiconductor. Okay, sometimes if you have some external force that's applied, for example, voltage that's applied to the semiconductor, if this external force that's applied, it's actually not so high that it creates electron hole pair. Okay, that means it doesn't influence electron at hole concentration at all, right? Then approximately we can still assume the thermal equilibrium condition. Okay, in other words, we can use the thermal equilibrium electron at hole concentration to estimate values in the calculation, right? So, sometimes with external force, although strictly speaking, you should not be using the thermal equilibrium quantities. But if let's say the external force is actually not so high as to disturb the carrier concentration, then we can still approximately use the thermal equilibrium values. Okay, so that's still okay because it doesn't change the carrier concentration. Okay, so we find that in calculation, sometimes we do make this type of assumption. All right. Okay, so how do we actually calculate or determine the concentration of electrons and holes in a semiconductor at thermal equilibrium? So it turns out that there's actually two parameters that we need to know, or two quantities that we need to know. The first is the density of states, which essentially describes the number of states that's available per unit volume of the crystal per unit energy, okay, in the conduction and the valence band. So in other words, it's kind of like the number of states that's available to take electrons and holes. All right, because if you know the number of states that's available, then it allows you to estimate the number of electron and holes that's present, right? If you also know the probability that each of these states is occupied by electron or not, okay? And that brings us to the second parameter, right, which is the probability that the state is occupied by electron. Okay, we know the number, how many like empty seats you have, and what is the chance that each seat is occupied by electron. Then you can do some estimation, right, of the number of electrons that is in the state. It's kind of like statistics, right, finding the expectation of a random variable for those who have done this probability and statistics, okay, in your math course. Okay, so it's kind of like finding the average or the expectation of a variable. Okay, so we're going to first start by talking about this probability first. Okay, we're going to describe this first, then we'll move on to the density of state. Okay, so the probability that a state is occupied by an electron, okay, at some temperature T, is actually described by this function called the Fermi-Dirac distribution function. Okay, it's a quantum mechanical sort of distribution function that is used to describe electron over some energy levels at thermal equilibrium. And this probability function has this underlying assumption, which is that electron has this quantum nature, right? This quantum nature electron is actually taken into account in the Fermi-Dirac probability function. And in the function itself, it also assumes that electrons are indistinguishable. Okay, it doesn't distinguish between electron A or electron B being present at whatever state. Okay, they don't care. As long as it's an electron, that's the probability, right? So it doesn't care about whether it's A, B, or C, or whatever. Okay, so it doesn't distinguish between electrons. Now, of course, the other important principle that is also applied here is the Pauli exclusion principle, in that at each quantum state, you can only have one particle, right? You cannot have two particles sharing the same quantum state. So in quantum mechanics, this is actually forbidden, right? So this is how the Fermi-Dirac distribution function actually looks like. It's actually kind of like a reciprocal function, where in the denominator you have 1 plus exponential, right? This exp is exponential, E minus df over kBt. The E here refers to the energy of the electron that you're considering, right? So this is a variable, and this EF is a quantity called the Fermi energy level. So for now, you can think of this as some reference energy level, okay, that is kind of fixed in a semiconductor. Okay, it's a reference level. Kb is a Boltzmann constant. Okay, Boltzmann constant is basically just a physical constant. The Boltzmann constant, if you refer to the table of physical constant, right, it has a value of 1.38 by 10 to the power of minus 23. Okay, and the unit for this Boltzmann constant is joules per Kelvin. Okay, that's your Boltzmann constant. And the other important part here is the temperature. Okay, it's the temperature T. Okay, so this Fermi Dirac probability function, right, basically tells you what is the probability of finding an electron at a particular energy state E. Okay, it gives you the chance that this energy state E is occupied by an electron. Okay, it basically tells you that what's the chance that you'll find an electron there. Just to sort of give you a better feel of what this Fermi Dirac distribution function is. Now, if you consider the limiting case where there's no thermal energy, temperature is 0 Kelvin, right? If you set T equal to 0 Kelvin in the equation, you'll find that the Fermi Dirac distribution function, right, has a value of 1 if the energy is less than the Fermi level, and it has a value of 0 if the energy is more than the Fermi level, okay, which is illustrated in this graph here. Right, below EF, the FE value is 1, and above EF, the FE value is 0. So how do you get this 1 and 0? You can actually do the calculation yourself in the limiting case. So I'm going to perhaps just go through one of the case, and the other one you can go and prove it yourself, right? Okay, let's consider a case where energy is less than EF. Okay, so notice that this exponential function is in the denominator, right, of this reciprocal function. So if E is less than EF, then you find that this term here in the exponential function will be negative, right? Because if E is less than EF, you subtract EF from E, you're going to get a negative value, okay? And this temperature here in the denominator, okay, if you set it to 0 Kelvin, that means this term here will become 0. And this is in the denominator, right? So if we take the reciprocal, okay, the whole thing actually will tend to negative infinity, right? Okay, you tend to negative infinity. So if the term within your exponential function is negative infinity, if you take exponential of negative infinity, what do you get? Anyone? This will tend to, how does the exponential curve looks like?
0.
0, yes. So if you draw the exponential curve, right, say y, then it looks kind of something like that, right? And if you go to negative infinity, which is to the left, the curve actually tends to 0. Okay, so e to the power minus infinity actually will tend to 0, which means that this term here is negligible, right? So if this term disappears, what you're left with is 1. If you take a reciprocal of 1, you get a value of 1. Okay, that's how we get this. So I'm going to leave this second part here to you, right? You go and work through this and see whether you can convince yourself that if you set E to be greater than EF at 0 Kelvin, you actually get 0 value for the Fermi Dirac distribution function. Okay, so go and sort of figure it out yourself. Okay, if you have any questions, come to tutorial and ask, then we can go through, all right? Okay, so in this case, what you find is that the Fermi Dirac distribution function is having a value of 1 at energy less than EF and 0 above EF. So if you look at a physical system like this, right? Okay, let's say I have some electron system with a few different energy from E1 to E5. And let's say at each of the energy level, you have this different number of states, okay, represented by this cup that you see there. So each cup is one state. And suppose we have so many number of electrons, right, in this system. Now at 0 Kelvin, right, at 0 Kelvin, remember we say that all particles will tend to go down to the lowest energy level possible, right? They'll tend to roll down. If there's a state, they will go, right? If you put a ball on a slope, the ball will roll down. Okay, they always go to the lowest energy level they can find. So under this condition, 0 Kelvin, you expect all the electrons to occupy the lowest states possible. Okay, so you find that they will take out all these states, and anything above that, right, you don't have electron occupying. So if you look at this Fermi Dirac distribution function and compare it to this electron system here, where do you think is the Fermi level? Where do you think is the Fermi level? So obviously the part where the state has an electron, what's the probability of electron occupying those states? 1, right? 100%, because you see that there's 1 there on each of the state. So for example here, the electron is occupying the state. What's the chance of finding an electron there? 100%. So probability is 1, right? And similarly, if you go to higher energy levels, right, there's also electron there. Probability is 1, right? At this level here, also probability 1, right? Can you see now that this corresponds to kind of this portion here, the low energy level below EF, and you come to the highest one where it's still occupied as E4, and when you go above it, E5, what can you say now? What's the chance that the electron actually occupy, let's say, a state here?
0.
Right, because you don't find any there. So the chance of finding electron there is obviously 0, which then will correspond to this part here, right? Okay, so the Fermi level is kind of like in between the part where it's all occupied and the part that's not occupied. So, I would say the Fermi level is kind of in between the E4 and E5, right? That's your EF.
So I have a question.
Yep.
So the EF here in the right-hand diagram is 4. Is it like a constant one or what?
Well, I would say it's in between.
So so the EF is 4 or what or something, or it is different in different situations.
It will be different in different situations. So in this particular consideration, take note that the condition is that the temperature is 0 Kelvin. In fact, if it's not 0 Kelvin, this EF will change.
Oh, so it will go up. So the F is not a constant.
The EF is not a constant. Yes, it depends on the system and the temperature and all these things.
It's just the energy level, is it?
It's okay. Hang on. Okay, in terms of temperature, actually, it would not change its position. Actually, it would change under different condition, which we'll talk about in a while. But at least at this stage, right? At this stage, you need to understand that the Fermi level is kind of the level where it's sort of between the transitions where you have the states that are occupied to the states that is not occupied.
Okay, thank you.
Yeah. Okay. So
hello, Professor.
Yep.
For the formula, if you sub in F equals to Fermi level, then you will get half. But how do you explain that?
Okay, this one is later. Later we'll talk about it. Yeah.
Okay.
Yeah, later I'll cover that. I mean, at this stage, we look at the limiting case, right? The special case where temperature is 0 Kelvin, right? And I would like you guys to appreciate the correspondence, right, between the Fermi direct distribution function and a physical system like this. Okay, so because of the fact that the electron generally will occupy the lowest energy states possible, you will find that in the case of the Fermi direct distribution function, this part here is 100% chance of finding electrons there. So in other words, it's actually describing an actual physical electron system, right? At 0 Kelvin, it's telling you that for energy lower than some EF, the chance of electron occupying there is 100%, which is true, right? All the electrons will tend to go down to the lowest energy level possible. And the transition between occupied states to empty states, right? That's kind of described by the Fermi level, right? The EF. Okay, so the Fermi direct distribution function indeed do describe the physical system, okay, that in terms of behavior that you would expect at 0 Kelvin. Okay, that's what we're trying to highlight. Okay, so it's in agreement with your understanding at least. Okay, so now what happens when the temperature actually increases above 0 Kelvin? Then if we look at the same electron system, then you'll find that with now thermal energy, some electrons may gain energy and they could move upwards, right? And in doing that, what you find is that there's now some states where it's empty, it's no longer 100% occupied, like in this case also, because they move upwards. And the originally empty states at E5, for example, now starts to have some electrons there because there's now thermal energy that can move them up to those levels which initially, if there's no thermal energy, they will not be able to move up. They just stay at the lowest possible. Okay, and in fact, this is also reflected in your Fermi direct distribution function for non-zero Kelvin temperature. Okay, and we can kind of tell by sort of quickly analyzing this, right? For example, if your temperature is non-zero, then this term is some positive value, right? So if you consider energy now above, okay, let's say we consider E above EF. Okay, remember previously at 0 Kelvin, for E above EF, the probability of finding electron there is 0. Okay, if it is not 0 Kelvin and you have E greater than EF, then this term here will become positive, right? Because E is now greater than EF, so you get a positive term on the numerator divided by a denominator that's also positive. So this quantity here overall is positive. So if you take the exponential of a positive number, right, this value here will be non-zero, right? It's not 0, but instead it's some positive value greater than 0. And if we add it to 1, right? If you add it to 1, then the value that you get in the denominator will be a value that is greater than 1. And if you take reciprocal now, right? If you take the reciprocal of a value that is greater than 1, you get a value that is less than 1. Agree? So that means that for some energy state above the Fermi level, it's no longer equal to 0, but instead it's some finite probability that is more than 0. In other words, there's a finite chance that some of the states will be occupied by electrons. Okay, which is not surprising because if you look at the physical system itself, right, with thermal energy, this electron comes from lower states that manage to get up because of thermal energy. Okay, so the equation do properly describe this. So you can basically run through the same thought process, right, to think about what happened to the probability below the Fermi level, and you'll find that it's no longer 1, but it will be less than 1. Okay, so I'm going to leave it to you to go and work it out yourself. Okay, and in fact, for non-zero Kelvin temperature, when you substitute energy as EF, that means you try to find out what's the probability of electron occupying the state at EF. Right? If you put E equal to EF into the equation, your denominator exponential function, the term inside becomes 0. So exponential of 0 is 1. You add it to 1, you get 2. You take a reciprocal, you actually get half. Okay, so there's a 50% chance that the Fermi level is occupied by electron. Okay, so in fact, another definition of Fermi level, right, is the energy level in an electron system in which the chance of finding electron there is 50%. Okay, so that's kind of like a formal definition for Fermi level. So in a way, you can think of it as like a reference level where there's a 50% chance that an electron can be found there. All right. In fact, if you sketch the Fermi direct distribution function now for non-zero Kelvin temperature, remember for 0 Kelvin temperature, we actually get this step function, right? This dotted curve that has a sharp transition, right, at the Fermi level, and then it drops to 0 at energy above EF. Okay, so that's for temperature equals to 0 Kelvin. And in fact, if we increase the temperature here to T1, for example, remember just now I say that for energy above the Fermi level at non-zero Kelvin temperature, you actually have some finite probability of finding electrons at those levels. Okay, so you expect now this part of the curve to be not 0 anymore, but it has some finite values. Okay, so there's some gradient there now. And similarly for energy level below EF, you find that it's no longer 100% because remember some of the electrons at those locations has a chance to move up. So if they move up, then they're going to leave behind empty states. Okay, so the probability of finding the states being occupied by electrons will be lesser. Okay, so you find that this curve also drop down. Okay, so the overall curve shape actually looks something like that. Instead of a sharp transition, you now have this sort of gradual profile, okay, at EF. And in fact, at EF, the probability is still half. Okay, so this basically tells us that the EF doesn't change the temperature, right? If you increase the temperature to even higher values, then you get this curve taking on a more gradual change in gradient, which again you can understand by the fact that at higher temperature, more and more electrons can move up to higher levels, right? So that's why you see this curve now extending more into the higher energy levels, and the non-1 values actually extend further deeper, right, below EF. Okay, so as you increase temperature, this actually smoothen out to a more gentle gradient, indicating that there's more electrons that can go up to higher energies, and also indicating that at lower energies, you're going to have more empty states because they have moved upwards, all right? Turns out that this Fermi direct distribution function also have this symmetrical property at the Fermi level, right? If you look at the curve, it's actually symmetrical about the Fermi level. And this is actually something that you can also prove, okay? And it's actually a tutorial questions that we would like you to think about in terms of the proof, okay? Okay, so that's the property of the symmetry at the Fermi level, right? If you have a symmetry about the Fermi level, EF, then what we can also say is that the probability of finding electrons at an energy state delta E above EF, which is this position here, right? Probability, that means this vertical value, is the same as 1 minus the probability of finding an electron at an energy state delta E below EF. So if you go backwards from EF by delta E, right, then this difference here, okay, this amount, subtract from 1, which means this value here, right, must be equal to the probability of finding an electron at an energy state delta E above EF. So in other words, this quantity here is equal to this quantity here, which is what you expect if it's symmetrical. Okay, so this is one of the relation that you can deduce for a symmetrical curve about some point. All right, so anyway, the tutorial question, one of the questions requires you to prove this symmetry. Okay, so you try and think about how to prove this, and we're going to discuss that in class, in the tutorial class. Okay, so here, this one is actually quite straightforward. You just start with, for example, the right-hand side, right? You put in the Fermi direct distribution function, show that left-hand side is equal to right-hand side. So similarly, I'm going to leave this to you to go and work it out after the class. Okay, see whether you can get the proof. Okay. Now let's look at an example to see what sort of values you're going to get for calculating the probability from the Fermi direct distribution function. So in this case, we have an energy state that is 0.56 eV above the Fermi level. And we're asked to determine what's the chance that this state is occupied by electron for two temperature values, 0 degrees Celsius and 100 degrees Celsius, right? So for energy state at 0.56 eV above Fermi level, then the energy that we're looking at is EF plus 0.56, right? So it's E equal to EF plus 0.56. If you put this into the Fermi direct distribution function, the EF will cancel out, right? And that leaves us 0.56 EV. And to calculate the numerical value, okay, take note that here we have to convert the units to joules. Okay, so whenever you do calculations like this, important thing to take note is that the units in your quantities that you're using, right, must be consistent with one another. Okay. If you think about it, in the denominator, what is KB? KB is a Boltzmann constant, and what did we say about the unit of KB? Okay, if you remember, right, just now I mentioned that KB has units of joules, Kelvin, and this temperature here, excuse me, this temperature here that we're going to substitute in, we also have to express it in Kelvin. Okay, it has to be consistent with the units of kb that you're using. All right, and similarly, in the numerator, this energy term has to be consistent with the energy term in the denominator in kb, which is in units of joules. So in other words, to calculate this quantity here, we need to actually convert the energy that we put here, right, to units of joules. We cannot leave it in EV, right? If you leave it in EV, the units are not compatible, and you just divide like that, your answer will be totally off. Okay, so wherever you do calculation, especially in the equations that we are using in this course, you have to pay attention to the units to make sure that you're using sort of compatible units. Okay, so that's why here we have to multiply by 1.6 by 10 to the power minus 19, because remember 1 EV is the energy that an electron gain in crossing a potential difference of 1 volt. So the charge of an electron is 1.6 by 10 to the power minus 19. If it crosses 1 volt, that means the energy that it gains will be the charge multiplied by 1 volt. Okay, so if we do that, then you get 1.6 by 10 to the power minus 19 joules of energy. Okay, so 0.56 EV will correspond to 0.56 multiplied by 1.6 by 10 to the power minus 19 joules of energy. Okay, so the conversion is very important, right? You can go back and try. If you don't convert and you just divide, you can compare like how much difference is the solution. The answer will be off by a few orders of magnitude. Okay. So anyway, if you do all this correctly and at 0 Kelvin temperature, 0 degrees Celsius temperature, which corresponds to 273 Kelvin, okay, then you can basically find out what's the probability. In the case of 0 degrees Celsius, the probability is extremely small, only 10 to the power minus 11, right? When your temperature is 100 degrees Celsius, which corresponds to 373 Kelvin, you find that the probability now goes up to 10 to the power minus 8. Although the value is still very small, but this 100 degrees change in the temperature actually resulted in 3 orders of magnitude of change in the probability. So it's 100 times more now, okay, at 100 degrees Celsius. Okay, so you can see that this probability, right, of finding electrons at some state, it's actually very sensitive to temperature. Okay, so in this case, it's like more close to 600. When I say 3 orders of magnitude, I'm just estimating. Okay, so in reality, it's about 600. But anyway, the key point here is that this probability is very sensitive to temperature. Okay, because there's a temperature term, right, in your equation. Right. Okay, so now the other quantity that we need to know to basically calculate the concentration of electrons and holes in the conduction and the valence band, holes and electrons in the conduction and valence bands, is this density of states, right? So generally speaking, the density of state, as you mentioned, refers to the number of states that's available, okay, per unit volume, per unit energy in a semiconductor. So you can think of it as like seed that's available at each energy level, right, that can take an electron. So in order to derive this density of state, in fact, the way we do this is first by considering free electrons, right, in three-dimensional space. And if you work through the derivation, which is not required in this course, but anyway, we put it in Appendix B for your reference. Okay, so if you're interested to see how it's derived, you can go and have a look for reference, but we do not require you to know how to derive, okay? So here, if you can actually derive the density of state in the case of free particle or free electron, and if you follow through the derivation, you find the density of state is given by this equation here, 4 pi, and then you have a mass quantity 2m to the power 3 over 2 divided by h cubed. And notice the dependence on energy is square root of E. Okay, so in other words, the density of state for a free particle or free electron has a root E relation, right, to energy. It's a square root relation to energy. And of course, the energy in the case of free electrons, as you have kind of determined before, right? Described in terms of wave vector is h bar square k square over 2m. If you put this in, right, you can replace the E with the wave vector quantity, and we can get a density of state in terms of wave vector. Okay. Of course, in the case of electron in a crystal, it's straight speaking no longer a free electron, right? But remember previously we say that in the case of electron in a semiconductor, the EK relation is still approximately parabolic near to the conduction and the valence band edge. Okay, so what this means is that in fact we can kind of still approximate the behavior of electron like a free particle, except that the mass that we need to use is no longer the rest mass. Okay, we need to use a mass that is equivalent to its interaction in the lattice, in the crystal. Okay, that is, we have to use the effective mass quantity, right, to describe this electron. And because of this approximately parabolic relation, okay, we can actually still use this density of state derivation for free electron. Because remember, for free electron, free particle, right, the energy against the momentum relation is actually parabolic. In other words, if you have some particle system which you know that the energy against the momentum is a parabolic relation, the solution will be of this form, right? Because this is derived based on the premise that we are dealing with free electron, or that the EK relation or energy against momentum relation is parabolic. Okay, so this equation will hold if you have a parabolic relation between the energy and momentum, which is in fact the case for electron in a crystal, for those that's near to the conduction and valence band edge. So as an approximation, we can actually just use that solution, right? Okay, that's what we mean here. But of course, in order to use that solution, we need to make some modification, right? Of course, the first one we mentioned is that we need to use the effective mass quantity instead, because electron in a crystal is no longer rest mass, it's some effective mass quantity, okay? And the other thing that we need to also adjust a little bit is the energy quantity. Because if you look at the conduction band, for example, notice that the conduction band edge is not at the zero value, right? In a classical free particle, if you look at the EK relation or energy against the momentum relation, the E against the momentum, right, the P, is such that the minimum point is at the zero value, okay? Whereas in this case, it's not at zero value, so we need to take into account that, right? We take into account that by shifting it down, right? We do a E minus EC, okay, which is the one that has this parabolic relation, right? So if you shift it down by EC, then this energy quantity here would have a parabolic relation with wave vector. Okay, so in other words, you have to write down the equation of this and find out what's the relation between E and EC. Okay, so which means that the energy that we're going to use for the case of electron in a semiconductor is no longer just E, right? Because you want to use the expression for classical particle, you need to adjust it to match the condition. Okay, so in this case, we have to shift the energy down by EC. Okay, so we replace the E with E minus EC, right, which is this here. And notice that the mass, we replace it with effective mass. So if you do that, then we can use this as a sort of approximation to the density of state in a semiconductor. Okay, so similarly, you can do the same for the valence band. And in this case, it's the other way, right? You actually do a EV minus E, because notice that in this case, the valence band is an inverted parabola. So you have to you have to flip the E first, right? You flip it, and then you shift it down by EV, okay, to get a parabola that is starting at zero value. So you have to do a minus E plus EV, okay, in order to replace the E with minus E plus EV, which will then have that parabolic relation. Okay, so the density of state in this case, in the valence band, the form is the same, except that in the energy quantity, right, in the square root term is EV minus E. Okay, you need to flip it to the same as the solution for a free particle. And similarly, we need to use the effective mass of holes in this equation. Okay, so this is actually a kind of an approximation, right? Because there's some equivalence between electron or hole in a semiconductor to a free particle in terms of the parabolic EK relation, right? We can use actually solution from classical solution, okay, to try and work out what is the solution for this quantum mechanical particles. Okay, so if you plot the graph of energy against the density of state for conduction and valence band, okay, these are the two curves. It's a root E relation, right? Okay, but take note that in this case, the density of state is plotted on the horizontal axis and the energy is on the vertical axis. Okay, the conventional way we draw graphs, it's if you think the G is the Y, right? Right, if the G is the Y, it's on the vertical and the energy is on the horizontal. Okay, if you plot the root E, then it's supposed to go something like this. Okay. So in this case, we flip it around. That's why it's curving a little bit differently than what you expect. Okay, because the axis is actually flipped. So so in this case, in the conduction band, we have this root E relation, right, going up. Okay, root E relation going upwards, and then on the other side, you have the root E relation going downwards. Okay, because for valence band it's EV minus E. So the curve actually flips downwards, all right? So above the conduction band, you have this increasing states that become available as the electron goes up in energy. And as you go down in energy, right, the number of states that's available will also increase, okay, according to this root E relation. And in between the conduction and the valence band, this is your band gap. The density of state there obviously must be 0, right? Because there's no states in the conduction band. Okay, so this part here, the curve is actually 0. Okay, that's your band gap. Okay. Now, with this information now, we can then go on to calculate the concentration, okay, of your electrons and holes. All right. And we do that by multiplying the density of states with the probability of finding electrons at those respective energy states, right? So to find the distribution of electrons at the various energy levels, we multiply the density of state, GC of E, with the Fermi direct distribution function, which tells us what's the chance of finding electron at that energy level. Okay, and if you actually do that, the product of the density of state, which is this curve, with the f of E, the probability of finding electrons in this range, right? If you multiply, then the curve that you get is actually this lump here, right? Okay, so this curve, okay, this curve here is essentially the solution for the number of electrons at each energy state. Okay, so this values here corresponds to electrons you can expect to find at those energy level. Okay, that's why it's written as a function of energy, right? It's a function of energy. Of course, in reality, when we look at electrons in the conduction band, we're actually not bothered with which energy level they are at, okay, but rather how many there are in the conduction band. So really, the parameters that we're interested in, right, it's more the sum of all these numbers, right? The sum of all these electrons you can find, or in other words, in a limiting case, we're interested in the total number of electrons in the conduction band, okay, which would essentially corresponds to the area under the curve. Okay, so in other words, to find the total number of electrons in the conduction band, we actually integrate, okay, this N0 function from EC, conduction band age, to infinity, right? You go all the way up as far as you can, okay? Right? So if you do that, then you can find out what's the total number of electrons that is present in the conduction band. That's the mathematical way of calculating, okay? So, of course, to solve this, you need to put in the equation for the density of states and the Fermi-Dirac distribution function here, right? And do the integration. So, okay, this integral here is actually not something that's very straightforward to calculate, you know. But in fact, if you make some assumption in terms of where the energy is, right, we can actually simplify those expressions so that when you solve it, you get an analytical equation, right? The solution is an analytical expression. If not, it's quite challenging to solve, and in fact, you may have to resort to numerical methods to find a solution, right? So the assumption that we're going to make is that you know, the Fermi level, okay, the Fermi level is quite far away from the conduction band edge, okay? If you make this assumption, right, the assumption that I'm trying to make here is that the Fermi level is quite far away from conduction band edge. Okay, that means EC minus EF, right? The difference between the two is much greater than KBT. Okay, it's much greater than, this is kind of like some thermal energy value. So it's much greater than that. We can actually use a specific value, let's say 3 KBT as a reference, to say that if the difference between the conduction band edge and the Fermi level is at least 3 KBT, then we can treat it as being quite far away from the conduction band edge. Okay, so if this condition is true, right, if this condition is true, then we can actually simplify the Fermi-Dirac distribution function to a simpler form, in the sense that, okay, if we go through the discussion, right, E minus EF, if it's much greater than KBT, then you're dividing by KBT, right? So this will imply that this value here will be greater than 1, right? So if it's greater than 1, and you take the exponential of it, okay, this whole thing will be large, will be much greater than 1. If it's much greater than 1, then this 1 here becomes negligible. We can throw it away, and we can approximate this Fermi-Dirac distribution function as exponential of minus E minus EF over KBT. Okay, in other words, because here, under this limiting condition, right, we have actually established that the 1 is actually negligible. Okay, so it's just 1 over exponential of E minus EF over KBT. You bring the exponential up, you get just exponential minus E minus EF over KBT. Okay, so you get just one single exponential function. This will help to simplify the calculation by a lot. Okay, because then you don't have to deal with reciprocal of exponential function. You know, it's harder to integrate. So if you put this back into the integral, right, and you actually solve it, in fact, even that is not straightforward to solve, you know. At this stage, you won't have enough mathematical foundation to solve it in terms of the integral, right? If you do solve it, okay, which again is not expected in you, if you do solve it, you find that the number of electrons, total number of electrons in the conduction band per unit volume, the N naught, is given by this solution here, okay, NC multiplied by exponential minus EC minus EF over KBT. This NC here is a term that is related to this here, right? If you solve it, it will come out from a solution, right? And you get this term from solving the integral as 2 pi effective mass KBT over h square, and the whole thing to the power 3 over 2 multiplied by 2. Okay, this come out from solving the integral, and we basically represent this by NC. Okay, so this NC term here is known as the effective density of states in the conduction band. Okay, so that's the solution, which will tell us how many electrons you can expect to find in this semiconductor with this Fermi level and at this particular temperature. Okay, so that's what the equation allows you to calculate. All right. So similarly, if you want to find the number of holes in the valence band, we carry out the same approach, but we need to modify a little bit. So in the case of holes, right, we multiply the density of state with the probability of finding holes in the valence band. Okay, So the number of the probability of finding holes in the valence band is simply 1 minus f of E, okay, the probability of finding electron. So if you do a complement, 1 minus f of E, this gives you the probability of not finding electrons at a state in the valence band. So if you don't find electrons, then it must be a hole, right? Okay, so this 1 minus f of E gives you the probability of finding holes at a particular energy state. And if you multiply this, then the curve that you get is kind of similar to the conduction band one. Okay, it's still kind of like a lump here, right? So the curve that you're multiplying, right, it's actually 1 minus f of E, which is going to be something like this. Okay, the blue one that you see is f of E, right? If you do a 1 minus f of E, you actually get this red curve. Okay, so it's actually multiplying the red curve and this density of state GV in the valence band. So you multiply the two, you get this curve here, this lump. So similarly, to find out the total number of holes in the valence band, okay, in other words, we're interested only in the area of the curve, right? We need to integrate. We need to integrate this whole distribution function, right? Integrate this function here. And again, right, if you make the assumption that the Fermi level is quite far away from the valence band edge, and using EF minus EV as a good reference of more than 3 kBT, okay? So if it's at least 3 kBT or above, then we take it that it's sufficiently far away, right? Then we can similarly approximate the 1 minus f of E to a single exponential function, okay? And this will help you to simplify the integral, right? Easier to solve for the integral. Okay, so this is essentially just approximation. Again, I'm going to leave it to you to go and convince yourself that that's a correct approximation. Okay, in the case where EF minus E is much greater than KBT, right? Then we can approximate to just a single exponential function, which, like the case of electron concentration, if you solve it, you get another expression, okay, that describe how many holes you have per unit volume in a semiconductor. Again, you get this term here in front of your exponential function, which is called the effective density of states in the valence band. And you notice that there's actually this effective mass of the valence band, right? Or effective mass of holes in the valence band. Okay, so these two sets of equations allows us to calculate the electron and hole concentration in a semiconductor if you know the position of the Fermi level, right? And if you know the temperature that they're dealing with. The rest of it are kind of constant. Kb is a constant. This EV is a semiconductor parameter, right? So all this you will know. And from there, you can actually calculate N0 and P0. Now, for these two equations, right, remember that it's essentially derived based on the assumption that the Fermi level is sufficiently far away from the conduction band edge and the valence band edge, okay? So that we can make those approximation. For this type of semiconductor that satisfy this condition, we call it a non-degenerate semiconductor, okay? The semiconductor that satisfy the condition where the Fermi level is not too close to the conduction band edge and not too close to the valence band edge are known as non-degenerate semiconductor. Okay, so for this non-degenerate semiconductor, we can then use this equation to solve for N0 and P0. Okay, the N0 and P0. If the condition is not satisfied, strictly speaking, you cannot use these two equations, right? Because these equations are derived based on the assumption that, that the assumption is valid. Okay, so strictly speaking, if it's not valid, you cannot actually use the N0 and P0. Strictly speaking, you should derive from scratch again, right, to satisfy the underlying condition. Okay, but of course, in certain cases, we may just use it to just apply to even like, slightly non-degenerate semiconductor to give you a sense of what sort of concentration that you're using. Okay. So Now, another important thing that you also need to take note is that in our derivation, right, we actually did not say anything about the semiconductor, okay, whether it's an intrinsic, a pure semiconductor, or a doped semiconductor. Okay, so in other words, these two equations that we have obtained, right, can actually be applied to both intrinsic and extrinsic semiconductor. Okay, and the other sort of key point is that this two expression has temperature terms in the exponential function, which means that it will be sensitive to temperature. Okay, because you have small change in temperature, and because it's an exponential function, the exponential function will actually amplify that change, you know, and you get relatively larger change in N naught and P naught. Okay, so you can expect N naught and P naught to be sensitive to temperature. Okay. All right. So okay, let's maybe take a 10 minutes break, and then we'll come back in a while to finish up the other half. Okay, let's go for a break.
Hi, Prof.
Yep.
So how do you define defect states?
How do you define defect states? Okay. Okay, defect states will be essentially the states that's introduced into the semiconductor due to imperfection in the crystal.
So this is an error in making the semiconductor, is it?
Yes, because in a practical sense, when you make the semiconductor, right? You know, in the ideal case, of course, you expect all the crystals to sort of fall into the lattice position and all that perfectly, lah. But in reality, you know, due to this manufacturing process and all that, there's always some chance that you may get additional electrons, you know, or sorry, additional atoms that is squeezed between atoms in the lattice position, or you could also have atoms that's missing from the lattice position. Okay, so this extra or missing atoms, right, would basically disturb the whole potential in the crystal, and this manifests in the form of a defect state into the Venn diagram. Right? If you think about it, it's kind of like, how do you get the Venn diagram of a semiconductor, right? You consider this periodic potential that is experienced by the electron, and then you put in the Schrodinger equation and you solve it, right? Now imagine if you have a missing atom at one position, then the whole structure in terms of potential will not be periodic anymore. At some point, it's missing, you know? And you put it in a Schrodinger equation and you solve it, will you expect to get back the same band structure? It won't be, right? There will be some something different already. So that difference basically manifests in the form of extra states in the band gap.
Okay. Great.
Yeah.
Thanks.
Okay. Okay, let's come back to our discussion. Okay, just a quick recap, right? So from our discussion just now, we see that we're trying to work out the concentration of electrons and holes in the semiconductor, right? We consider two quantity, the Fermi direct distribution function and the density of states in the semiconductor. We can actually derive two expressions to calculate the concentration of electrons in the conduction band and the concentration of holes in the valence band. And recall that this is basically derived on the assumption that the Fermi level is not too close to the conduction band edge and not too close to the valence band edge. Okay, and such a semiconductor material that satisfies this condition is known as a non-degenerate semiconductor. In other words, to use this equation, the semiconductor must be non-degenerate. Okay, if you have one that has a concentration that is too high, right? That is giving you a condition where the Fermi level is less than 3 kBT away from the conduction band edge or the valence band edge, then strictly speaking, these equations cannot be used. All right. So, of course, the other questions that you may ask is, why are we sort of interested to know about things like the Fermi level and all that? Turns out that the Fermi level allows you to understand the conditions in the semiconductor in terms of how the carrier would flow in the semiconductor. Later on, when you start to learn about PN junction, right, you will see that when you put two semiconductor materials in contact at thermal equilibrium, for example, a P and N-type material that's put together to form a PN junction, at thermal equilibrium, the Fermi levels will basically align, okay? And in addition, the current that is flowing in the semiconductor, it's proportional to the gradient of the Fermi level as well. So this gives information about current that is flowing in the semiconductor. Okay, so that's why there's a need to be able to describe Fermi levels, concentrations in the semiconductor. Okay, so for the remaining part of this discussion, we're going to see how we can use these two expressions that we have determined to work out some other quantities in the semiconductor. Now let's start with the intrinsic semiconductor material, the pure semiconductor. And we mentioned that the electron concentration and the hole concentration are basically equal, right? So, and we also denote the concentration of electrons and holes as Ni and Pi, okay, with the subscript of I to indicate that it's referring to an intrinsic semiconductor material. And the Ni and Pi are essentially equal because in a pure semiconductor, for any electron that's created, it would also create a hole, right, at the same time. So using the two expressions that we have derived, okay, and we apply it to intrinsic semiconductor material, we can basically modify the N0 to Ni because we're talking about a pure semiconductor. And the other thing that we need to change is your Fermi level. So in this case, if it's a pure semiconductor, we use EI to represent the intrinsic Fermi level in a pure semiconductor. Okay, that gives us a set of, or rather, this equation. Okay, that it's applicable for pure semiconductor material. So similarly, if you do the same to the whole expression, replacing the P0 with Pi and EF with EI for intrinsic semiconductor, you get similarly this expression that you can use. Okay, so these two equation is kind of like a subset of N0 and P0, right? It's specifically for pure semiconductor. If you now try and multiply Ni and Pi together, okay, so here what we're doing is actually multiplying Ni with Pi. Okay, but in the case of pure semiconductor, the Ni and Pi are the same. So this simply is just Ni square. And if you put in the expression that we had in the previous slide, then you get NCMV and exponential of EC minus EV. Notice that the EI actually cancel out. And what is EC minus EV? Is basically the difference between conduction and valence band, okay, which is essentially the band gap of the semiconductor. Okay, so this EC minus EV is really just EG, which is the band gap of the semiconductor. Okay. And of course, if we bring over the square to the other side, then we basically have an expression for the intrinsic carrier concentration, which is given by square root NCMV exponential minus EG over 2 kBT, right? The 2 here comes from the square root, okay, square root of exponential, which goes in as a half. Okay, so this expression here basically allows us to calculate what is the intrinsic carrier concentration in a pure semiconductor. And notice that it depends on temperature, right? There's still a dependence on temperature. And the other important parameter is actually the band gap, EG. Okay, it just depends on these two terms, the temperature and the band gap. And this is actually something that is not surprising also, right? Because if you think about it, how does the intrinsic carrier concentration in a pure semiconductor change with band gap? So if you think about it, right, if you have some particular band gap semiconductor and the electrons and holes are basically generated through band-to-band transition. Now what happens if your band gap is small? Okay, if your band gap is small at a fixed temperature, the band-to-band transition will result in a lot of electrons and holes, right? And if you analyze the equation, right, if your EG is small, that means it goes down. Notice that it's actually a negative value here. So if the magnitude goes down, that means this quantity in the exponential term becomes less negative, right? In other words, the value increase. It becomes less negative, then the exponential value will actually increase, which implies that your Ni will also increase. So this is consistent with what you expect if you analyze it logically, right? Because the smaller band gap with the same temperature, it's easier for the electron to go out to conduction band, and you expect more to do that. Electron and hole concentration will basically go up. Okay, so this expression do explain this change in the concentration. So you can do the same analysis for temperature. It should be consistent with what you expect. Okay, so if you also use the electron and hole concentration for a general semiconductor, right, not just pure, that means you use N0 and P0, and you multiply it together, then you find that it similarly gives you an expression, okay, that is the same as the pure semiconductor, okay. This NCMV exponential minus EG over kBT is actually the same as what you get with Ni square, right? So we look at Ni square, you know, the expression that we get is the same as N0 P0. Okay, so this allows us to actually write down another expression, which is N0 P0 equals to Ni square, relating the concentration of electrons to concentration of holes via the square of the intrinsic carrier concentration. Okay, so this equation here is sometimes called the mass action law, right? It describes the relation between electron and hole in a semiconductor. Okay, that's a mass action law. And you know, similarly, it's valid for both intrinsic and extrinsic semiconductor because you did not make any assumption on this. So this is actually a very convenient expression, which in fact later on we're going to use to calculate N0 and P0 in a general semiconductor. Okay, so this is an equation that actually we use quite frequently. Okay, so let's try and do some calculation for the intrinsic carrier concentration. So in this example, we have silicon at 300 Kelvin, and we're interested to find out what's the intrinsic carrier concentration of silicon. That means in a pure silicon material. So if we look out the properties of silicon, right, you find that the effective mass, these quantities are actually known values, right? It's been characterized. effective mass of electron in silicon is 1.08 of rest mass. Effective mass of holes in silicon is 0.56 effective mass, rest mass. And the band gap of silicon is 1.12 electron volt. And using the expression for effective density of state for conduction and valence band, okay, which relates to several parameters, including effective mass, right? You can calculate what are those values at the temperature of 300 Kelvin. Okay, so for NC, you should get 2.8 by 10 to the power 19. For MV is 1.05 by 10 to the power 19. And using the expression for intrinsic carrier concentration, you should get a value of around about 6.84 by 10 to the power 9 per cubic centimeter. Okay, in fact, this is very close to experimentally determined value of 1.5 by 10 to the power 10. Okay, this slight difference is due to the simple theoretical model that's used to arrive at the equation. Okay, but generally speaking, the values it's quite close. So if you compare the intrinsic carrier concentration of different semiconductor material, okay, as listed in this table here, for silicon, just now we see that it is around about 10 to the power 10 per cubic centimeter, with a band gap of 1.12 or 1.11 EV, compared to bigger band gap semiconductor like gallium arsenide, which has a band gap of 1.43 or 42. You find that the intrinsic carrier concentration is smaller. So again, this is not surprising, right? Because if you have a semiconductor that has a larger band gap, at the same temperature, the barrier is larger. So the band-to-band transition, in this case, will be lesser, right? And you expect the number of electrons and holes that's created to be smaller than that of silicon with a smaller band gap, because the barrier is larger, okay? And conversely, if you look at a narrower band gap semiconductor like germanium, okay, germanium has a band gap of 0.67 or 0.66, depends on which reference you look at. Notice that the intrinsic carrier concentration is significantly larger, 10 to the power 13. Okay, so it's actually more. So, yeah, so this is kind of how the intrinsic carrier concentration varies between different semiconductor material. Now, in fact, using this intrinsic carrier concentration expression, okay, you find that we can actually rewrite the expression, okay, such that we substitute in the NCMV, and we have this effective mass term, and there's a term that contains temperature T, and of course the exponential term has a temperature T there as well. Now, if you look at this expression here, although there's a T in this term here, right, multiplying the exponential term, this T here would have a lesser influence on the Ni because it's only T to the power of 3 over 2. Whereas the T that's in the exponential function would actually have a larger influence, in the sense that a small change in this T here will actually result in quite a big change in the exponential value, okay, because the exponential function amplifies the change, right? And if you make an approximation that, this term here is relatively constant, although your temperature could be changing, right, then we can treat this whole part here as a fixed value, okay? So if you make the assumption, then we can write Ni as a constant multiplied by exponential minus Eg over 2 kBT. And if you apply natural log on both sides, we can write this as a straight line equation, where on the left side you have a natural log of Ni, okay, which is like your Y quantity, right? And then you have this constant, which is natural log, which will give it still a constant, right, like a C value. And the exponential term now becomes Eg over 2 kBT. Okay, so this last term here has this variable of temperature. So you can think of this 1 over T, right? The 1 over T here can be treated as the variable X. Okay, so using this straight line equation, if you change the temperature and you measure the intrinsic carrier concentration change in the semiconductor, which is something you can do, then you can plot this as a straight line equation. That means you take a different temperature and you measure different Ni. You can plot this as a straight line equation, right? You will get a straight line where the y-intercept is your ln C value, right? And the gradient of your straight line equation is actually Eg over 2kb. In other words, if you actually do this experiment, measuring how the Ni changes with temperature and plotting the straight line curve, you can find out the band gap of the semiconductor by determining the gradient of the straight line equation. Okay, so this is actually something that we do as well, to sort of measure the band gap of a semiconductor, okay, by changing the temperature, measuring the intrinsic carrier concentration, and plotting it as a straight line equation, right? So like you see here, so if you do that, the gradient actually tells you the band gap. And in the case of silicon, it has this particular gradient, and notice that germanium, it's a smaller band gap, so the gradient is more gentle, right? And gallium arsenide is a larger band gap. You see the gradient is actually steeper. Okay, so this is actually a common approach that's used to characterize the band gap of a semiconductor. Okay, so this is actually an experiment that we do regularly. Okay, right. So now another thing that we could do, right, with the equations that we have in terms of pure semiconductor is, other than multiplying the Ni with Pi, we can also equate Ni to Pi using the two sets of equations that we have, right? Or using the set of equations that we have for intrinsic material. So we equate Ni to Pi, where Ni is in terms of NC exponential, and all the EI and EC, right? If you equate that two and you simplify it, you can make EI the subject. Okay, you make EI the subject, and you find that the EI is given by the sum of two terms. Okay, the first one is half EC plus EV. The other term is half KBT and natural log of NB over NC. Okay, this half EC plus EV is essentially referring to, okay, if we think about it logically, we have EC, right? We have EV. Okay, so when you halve the sum of these two values, okay, let's say this is a zero value. So from here to here is EV. From here to here is your EC. If you add the two and you take the average, what do you get? You will get the middle of EC and EV, right? If you sum out the two and take the average. Okay, so in other words, this half EC plus EV is really the middle of the band gap. Okay, we denote that as EV. Now, what about the second term? Okay, the second term, half KBT, natural log NC, natural log NV over NC. We can substitute in the expression for effective density of state in the valence band and effective density of state in the conduction band. And this will give you a ratio of the density of, the effective mass of holes to electron. Okay, and in a sort of general sense, the effective mass of electrons and holes is, broadly speaking, quite similar in values, right? They don't differ too much. So if you treat them as approximately 1, right, because they're about the same, and you take the natural log, you actually end up with 0 or a very small value if it's not 1, right? In other words, this second term here is a quantity that is rather small. Okay, this second term is actually rather small. Okay, much less than 1. So this term here, it's in fact so small that we can actually consider it as negligible, right? We can actually drop it. Okay, we can drop it and approximate the EI as emit. Okay, so in most cases, right, we think of the EI as approximately equals to emit. Okay, because the second term here it's really quite small. Unless, of course, the question asks you to find out what is the difference between EI and emit. Okay, but if not, in general calculation, if you are using EI, you can just treat it as in the middle of the band gap. Okay, in fact, in the tutorial, one of the question requires you to calculate this gap lah. Okay, so just to give you a sense of how different is it between EC and emit. Okay, but by and large, this value it's pretty small. Okay. So again, this proof part, I'm going to leave it to you, right? If you equate Ni to Pi, okay, you're going to work it out yourself. Okay, just sort of expanding the expression and rearrange, find out what is EI. You should get the expression that we discussed. Okay, you should get this expression. Okay, so go and do it as an exercise for you. Right, so what have we sort of covered so far in the intrinsic semiconductor material, right? We've been doing a lot of calculation on intrinsic semiconductor material. So the last thing that we talk about is that, in fact, the intrinsic Fermi level is related to two terms, the middle of the band gap, and the second term, which we say is generally very small. Okay, so if you look at this illustration here, you notice that the difference between the emit and the EI, right, it's small. Okay, so most cases we can just assume that it's the same. All right, unless of course, like I say, the question requires you to calculate the actual separation. Okay, if not, you can just assume it's the same. With the N0 and P0 equation, these two here, okay, we can also see how the Fermi level would affect the N0. Okay, the position of Fermi level will affect N0. So we consider a case where the Fermi level increases in value, right? If you look at the N0 equation, for example, if the EF increases, that means it goes closer to the conduction band edge. It means that this value here will reduce. Okay, the magnitude will reduce, but because this is negative, that means it becomes less negative. If it becomes less negative, that means the exponential value increases, implying that the N0 increases. Okay, so the fact that the Fermi level go close to the conduction band would lead to an increase in the electron concentration. Okay, so we can figure this out through the equation. How about the effect on P0? Okay, we can also sort of think through similarly, right? If the EF move close to the conduction band edge, then the separation from Fermi level to valence band edge will increase. In other words, the EF minus EV will grow up in value. Okay, the magnitude will go up, and because there's a negative sign there, this quantity here become more negative. If it's more negative, the exponential value actually decreases. That means the P0 decrease. Okay, so in fact, if your EF were to increase, that means it gets nearer to the conduction band edge, you find that the N0 increases and the P0 actually decreases. Okay, so you can actually tell from this expression here, right? And conversely, right, if you consider the case where the Fermi level actually go downwards, closer to the valence band edge, then you will see the opposite trend for the N0 and P0. N0 will actually drop, and P0 actually increases. Okay, so this is what you can see from the equation. All right, so that's what we can infer so far from the equations that we have. Right. Okay, then another thing that we could do is with the N0 value, right, or the N0 expression. Okay, the N0 expression is expressed in terms of the effective density of, say, NC. We have an exponential. We have a minus EC minus EF, right? over KBT. Okay, that's our N naught. And of course, we have another expression for Ni, okay, which is also NC and exponential, in this case, minus EC minus EI, right? Sorry, I'm writing with a mouse, so the handwriting is horrible. Over KBT. So another thing we could do is actually to divide these two terms. Okay, we divide N naught with Ni. You find that the NC will cancel out. Okay, and if you combine the exponential function, you will also see that the EC will cancel out, and that just leave you EF and EI. Okay, this is EI. Okay, so you're left with EF and EI in the exponential term, right? And if you work that out, you will find that the N naught can be expressed in terms of Ni. Okay, can be expressed in terms of Ni, and exponential term containing the difference between the Fermi level and the intrinsic Fermi level. Okay, so doing the same for P naught with Ni. Okay, similarly, you can divide P naught with Ni, and you get another similar expression with Ni as the term multiplying the exponential function now, and this quantity inside is EI minus EF. Okay, so this is in fact another complementary set of equation that we could use, okay, together with the one that is expressed in terms of the effective density of states, okay, in your calculations of the concentration of electrons and holes. Then the question of which one to use really depends on what you have, right? If you know the intrinsic carrier concentration of the semiconductor, then obviously you will use this set of equation here, right? Because you know the values of Ni. On the other hand, if you know the effective density of states, then you can use the other set to try and find out what is the N naught and P naught. Okay, so these are really two complementary equations that we could use depending on what you have. And you know, together with the mass action law, right, N naught P naught equals to Ni square, we can effectively solve for the concentration of the carriers in the semiconductor, and we can solve for the Fermi levels, okay, in the semiconductor. All right. So this part here, which is kind of trying to prove N naught equals to Ni exponential EF minus EI over KBT, it's straightforward lah. Okay, so again, I'm going to leave it to you as an exercise to complete. Okay, just divide and cancel out the terms and rearrange. You should get this expression here. Okay, so I'll just leave it to you to fill in. So, okay, so just to sort of have an overview and conclude, right, what we have learned so far. In the case of a pure semiconductor, we see that the intrinsic Fermi level is approximately in the middle of the band gap. Okay, so in most cases, we just assume is equal to E mid. And of course, in this case, the N naught and P naught, okay, so-called N naught and P naught, is really your intrinsic carrier concentration, Ni. Okay. Now, if you increase, okay, if you increase the Fermi level and move it closer to the conduction band edge, we see from the equation, right, just now we mentioned that the N naught will increase. So in fact, if you use the Ni expression as shown here, right, if you have N naught expressed as Ni, and you rearrange this in terms of EF minus EI, okay, in N naught over Ni, right, if you have a higher concentration of electrons, if this goes up, then EF minus EI will increase. Okay, that means the EIF actually goes closer to the conduction band edge. Okay, so regardless of which set of equation you use, you come to the same conclusion, right? If your concentration of electron goes up, Fermi level goes up. Or conversely, if Fermi level goes up, concentration of electrons goes up. Okay, so you can see this from the two sets of equations. Okay, so similarly, right? Similarly, we also mentioned that the P naught actually decreases, right, when your EF goes up. Again, from the equation here, you can see here, right? If your N naught increases, Okay, if your N0 increases, your P0 will decrease. Why? Because from the mass action law, N0 P0 equals to Ni square, okay, is related to this constant Ni square, right? So that means the P0 is actually varying inversely to N0. So if your N0 is large, your P0 becomes small. So if the P0 is small, right here, then the difference between EI and EF also will be small, which means that you know, the Fermi level actually sorry, EI minus EF is small, and in fact it's negative actually. So it's the other way. And the Fermi level will be above the intrinsic Fermi level, okay, from this, which is consistent with what you expect in this case, right? Everybody get it? Maybe not so clear. Does anybody don't quite catch what I was saying in the last part?
Can you repeat?
Okay, so I repeat again. So we are looking at a case where the N0 is large, right? Okay, so we say that from the mass action law, P0 equals to Ni square over N0. Okay, if your N0 is large, then your P0 actually will become small because of the mass action law, right? And in fact, it's not just small. In fact, if your N0 is greater, right? If you see that your N0 is greater than Ni for a doped semiconductor, okay, you'll be greater than the intrinsic concentration. Then, in fact, what you find is that the P0 actually will become less than Ni, okay? If P0 is less than Ni, this term here will be less than 1. And if you take a natural log of it, you actually get a negative value. Okay, and what you can see here is that the EI minus EF will be negative, which means that the Fermi level is not below the intrinsic Fermi level. The Fermi level is actually above the intrinsic level. That's why when you subtract, you get negative. Okay, which is what you would expect, right? In this case, the EF is actually above the intrinsic. Make sense? Kenna, any question on this? Okay, so conversely, right, if you look at a case where you have now more P0, okay, we have more P0. In this case, we look at the P0 expression. If your P0 is now large, that means it goes up, then this whole term here become positive, right? And your EI minus EF is positive, meaning that your Fermi level must be below the intrinsic Fermi level. Okay, so which is what you expect here, right? And conversely, right? Conversely, if your P0 is large, right, then your N0 must be small because of mass action law. And similarly, right, you find that the P0 will be greater than Ni, okay, if it increases, and the N0 will be less than Ni. And in fact, you put into this expression here, right? Okay, you put into this expression, N0 now is less than Ni, which means that this will be less than 1. You take natural log, you actually get a negative value, which means that EF minus EI is negative, implying that the Fermi level must be below the intrinsic. That's why when you subtract EF with EI, you get negative. Okay, which again is consistent with what you see here. The EF is actually below the intrinsic Fermi level. Okay, so if you look at this sort of trend, right, for the N0 P0 with EF. Okay, so in this case, when N0 is large and P0 is small, we say that the Fermi level is above the intrinsic Fermi level. And looking at this, right, what can you say about this type of semiconductor? Your N0 is large, P0 is small. What do you call this type of semiconductor? You have more electrons and holes. This, in fact, refers to
N-type.
N-type, yes. Okay, so this is, thank you. So this is, in fact, referring to an N-type semiconductor, right? And conversely, you know, the other way around, right? When the EF it's below the intrinsic Fermi level, right? We see the reverse trend where P naught is now larger and N naught is actually smaller, and this will refer to the P-type semiconductor. Okay, so generally what we can infer here is that for N-type semiconductor, you expect the Fermi level to be above the EI or above the middle of the band gap. For P-type semiconductor, you expect the Fermi level to be below the intrinsic Fermi level or the middle of the band gap. Okay, so that's the in fact the property of N-type and the P-type semiconductor. The Fermi levels are at different positions. Okay, anyone has questions on this? So I think at this stage, you know, basically just get a general feel. You know, when you start to do the tutorial questions, I think, you know, you do a few questions, then I think it will become sort of you know, understandable after that. Okay, at this stage, you may feel. Yeah.
May I ask how can a P naught drop below intrinsic, like an intrinsic N?
How can it drop below the intrinsic? Because the okay, in the case of N-type, right? Because of the increase in electron concentration, it actually results in also increased recombination. So that increased recombination would reduce both the electrons and holes, and because the holes initially is at Ni or Pi, so with this increased recombination, it actually reduces the minority carrier to lower than Ni.
Oh, so what it means is like some of the electron like initially from the donor can actually drop back to the valence band.
Yes, yes. So again, it's a competition between the generation and recombination, right? The generation is mainly temperature dependent. The recombination, how fast they recombine, right? In fact, as you'll see later on, this is something that in fact we'll cover later on. The recombination depends on the electron and hole concentration. If your electron concentration, for example, is very large, that actually results in a higher recombination, which have to somehow balance with the thermal generation, right? So that they achieve equilibrium again. And that basically result in the originally Ni value for the minority carrier to drop below the Ni value, so that overall that generation and recombination balance again to get to thermal equilibrium.
Okay, I see.
Yeah.
Thank you.
Yeah. So later on, when we talk about recombination, I think you become clearer for this part. Okay. Anyone has any other questions? So I think in general.
It's
yeah.
Kind of a word with you later is about like the attendance taking.
Yeah.
During the online lecture.
Yeah.
Wait, so basically me and my friend were watching through like another friend's device. And so
okay.
that we were marked as absent without valid reason.
Well, I mean, this is one part of it, because you know, I'm not sure if you share, you can hear properly or not.
But like we after this, like we won't be watching on the same device. Like we've decided to all watch on separate devices. But I was wondering if we can request for our attendance for those two lectures to be changed. to present?
Sorry, the attendance for which one?
The 14th and the 21st.
To be changed?
Yeah, to like present. Like we're wondering if it could be done.
Oh, so did someone like ask you about it or what?
Yeah, someone, I think our school coordinator actually did approach us about
Oh,
it.
okay. Then okay, because this is so that's why it's also important that you sign your attendance on the link that was given to you lah every time you attend the class. So this attendance that I sort of download to give to our office, right? It's basically for them to monitor lah, because this is required by MOE. So if let's say you have valid reasons like you are actually looking on it with the same device with your friend, then you just tell your school teacher lah. It's fine lah. Just explain lah. Okay, no need to worry. As long as you can explain, it's fine lah.
So I just realized I didn't take the attendance.
Sorry, say that again.
I just realized I didn't take the attendance, but I'm here all the time.
Sorry, which one? Which one? The scan one or
the QR code? QR
okay,
code.
Okay.
I forgot to submit.
Yeah, okay. Then just remember to submit lah. Because the thing is, other than the QR code which you need to submit, right? I'm also downloading this as a backup lah. In case you forget, then at least this shows that you're there.
Am I gonna be marked as absent?
Well, as long as because I do download the list as well to give to our office, and as long as your attendance is there, it's fine lah.
So as long as I'm in the meeting, it's okay.
Yeah,
but I should submit the form, is it?
Yeah, the QR code one, you better go and submit lah. But of course you forget, I think it's still okay if you are actually physically in this online lecture, right? Because near the end, we'll also download and give them as a backup. Yeah, but for those, okay, it's fine now. So anyway, for those who are sharing a device to watch, right, for the lecture, again, it's just a thing that they are just tracking lah. If you have a reason, then just explain. It should be okay lah. But at the same time, if you also mark your attendance, that will be great also lah. So don't worry lah. I think the main thing is, if you have valid reason, just explain. Okay, no need to ask me to submit one that's modified. Then that's cheating already, right? I mean, in reality, you did not sort of sign in to listen, but you were sharing with your friend, then just explain it. Okay?
Prof.
Yeah.
So do we just not calculate EF, because EF will be given in the questions Fermi level?
Okay, so in terms of where you get the EF, right? In fact, the next lecture we're going to see how we can find it or how we can use it when it's given.
Okay.
So actually we can calculate it as well if you know the concentration, because all these equations are interrelated. If you know one, you can calculate the other. So that actually will be discussed in the next lecture.
Okay. Thank you.
Okay. Anyone else has anything to ask?
Hi, Prof. Can I ask, how do we check our attendance?
How do you check? As long as you are in, you don't have to worry lah. Because when I download, they'll capture whoever has signed in. So as long as you're in, you don't have to worry. You should be in there.
Okay, thank you.
And also do remember to go and scan the QR code and just sign in as a sort of additional precaution.
Okay, thank you.
Yeah, so unfortunately, this is something that MOE requires us to do, that to make sure that you guys do attend, because if you don't make a certain percentage of attendance, MOE can bar you from taking the exam, right? Okay, so do pay attention to that. Okay, so if there's no more question, I guess we can stop here for today. But anyway, just go back, look through again. If you have any questions, just feel free to ask during the tutorial. We'll be happy to clarify any doubts that you may have.
Prof.
Yep.
May I ask, for the density of states, the equation, what does H represent?
H is a Planck constant. It's a physical constant.
Okay.
Yeah, it's a fixed value.
Okay, thank you.
Yeah. Okay, no more question, then we can all log off lah. Okay, and try the tutorial before you come for class next week. And for those who have lab tomorrow, please do download and print a copy of the manual before you come for class. Okay?
Sorry, Prof. Which tutorial do we do?
Which tutorial? Do the next one, tutorial 2.
Okay.
Yeah. So follow the sequence. Generally, the lecture will be a little bit faster than the tutorial. So just go in the sequence because you just had one tutorial, right? So the next one should be tutorial 2.
Prof.
Yep.
When do we have to hand in the lab manual?
Hand in the lab manual. For which one?
For the most recent one.
Okay. The lab one, you do not have to submit your lab manual or your result sheet. That one is not required because the lab one is more to expose you to the equipment, so that's not graded.
Oh, okay. Thank you.
Yeah, so, but we still expect you to come because it helps in terms of familiarizing with the equipment. Because if you are not familiar, then you find that lab 2, lab 3, you'll be struggling with knowing how to operate the equipment. Then you may not have time to do the proper experiment. So that's why it's still important to attend the lab 1.
So, Prof,
Yeah.
will you be giving us a template for the next, like the reports we have to submit?
Yes. When we come to the lab 2, lab 3, during the session itself, we will brief you on what is required. And then we also show you some example so that you know what is expected.
All right, thanks.
Yeah. Okay, if there's no more question, you can log off. Thanks very much. See you guys tomorrow or next week.
Thank you, sir.
Right. Okay. Bye. Take care.
Bye.
Thank you, sir.
Okay. Bye.
Thank
Thanks,
you.
Prof.
Right. Bye.
Thank you. Bye-bye.
Okay. Bye. See you. Bye.
Thank you, Prof.
Okay. Bye.